A four-seat airplane just started flying, paying passengers commercially in China, and it doesn't burn a single drop of fuel. Not a test flight. Not a demonstration for investors. An actual government-certified aircraft called the RX-4E, cleared in December 2024, to carry real customers right now, today. While teams of former NASA and Boeing engineers in America have spent the better part of a decade and hundreds of millions of dollars chasing this exact same milestone, still waiting on regulators to finish the paperwork, a research lab in northeastern China quietly beat them to the finish line. The aircraft is already appearing at international air shows in Europe. It already has signed purchase orders from real airlines. And the company selling it worldwide is already breaking ground on a factory in the Middle East designed to churn out hundreds of these planes every year. If that sounds almost too fast to be real, stick around, because it gets stranger. Give this video a like. It takes serious research to put stories like this together. And subscribe so you don't miss what's coming, because the full story here goes deeper than a single certification. This aircraft solves an engineering problem that stumped aviation for 70 years, and the way it got built completely upends who most people assume is actually winning the race toward electric flight. But to understand why this particular plane matters this much, you first need to understand exactly what it's replacing, and why that older technology has been quietly getting more expensive every year. If you've ever climbed into a small airplane, there's a strong chance it was a Cessna. The Cessna 182 first rolled off the assembly line back in 1956, and remarkably, it's still in production today. Nearly 70 years running on essentially unchanged engineering. Credit where it's due, the 182 earned its reputation honestly. It's dependable. It's rugged. Pilots across the globe know its systems by heart. Land one on some remote dirt strip, and you'll likely find a mechanic nearby who's spent decades working on Lycoming engines. You'd be back in the air before lunch. That kind of trust doesn't happen accidentally. But beneath that trusted reputation sits a financial problem that keeps getting worse year after year. Walk into a dealership and price out a brand new Cessna 182 today, and you're staring at $550,000 to $650,000. That's an enormous sum for an aircraft whose core engine technology has barely evolved since the Eisenhower administration. And the costs don't stop at the sticker price. Every hour spent flying, that Lycoming engine burns roughly 14 gallons of aviation gasoline. At current prices, that's close to $100 in fuel alone, before maintenance, insurance, or hangar fees even enter the equation. Then there's the engine itself. Every 2,000 flight hours, the Lycoming requires a full rebuild, running $30,000 to $50,000 depending on parts and labor. Tally everything together: fuel, maintenance, insurance, hangar costs, and every other expense, and you're looking at $150 to $250 per flight hour just keeping a Cessna 182 airborne. Now imagine running a flight school. 5 or 6 planes flying 6 days a week. 4 hours daily, rain or shine. Before a single student pays you a dime, you're already underwater financially. You charge maybe $200 to $300 for a 1-hour lesson, but $150 to $250 of that goes straight toward keeping the plane running. After insurance, instructor pay, and facility costs, your margin sits near nothing. One unexpected repair, one fuel spike, one last-minute cancellation, and you're personally absorbing that loss. Then there's the lead problem, one regulators can no longer ignore. The aviation fuel powering Cessnas, called avgas, still contains lead, the same toxic additive pulled from car gasoline decades earlier for safety reasons. In 2023, the Environmental Protection Agency declared lead emissions from small aircraft a genuine public health hazard. Aviation fuel is now the last transportation fuel in America, still carrying lead in any meaningful quantity. And the unleaded replacements aren't cheap either, running roughly 30% higher than what they replace. Some airports in California already charge near $7 a gallon. So costs keep climbing, while regulations keep tightening and the fleet keeps aging simultaneously. Something eventually has to give. The electric aircraft we're discussing here burns zero fuel, meaning none of these problems touch it at all. But before diving into how it actually works, we need to understand why Western companies chasing this exact same goal haven't managed to get their planes certified yet. Electric aviation throughout the West is genuinely packed with talent. Engineers who walked away from NASA, Boeing, and SpaceX to chase battery-powered flight as their next challenge. Companies like Beta Technologies in Vermont and Buy Aerospace in Colorado have collectively raised hundreds of millions of dollars, assembled brilliant engineering teams, and actually built aircraft capable of leaving the ground under their own power. This isn't a story about Western incompetence. It's a story about what happens when you invent something entirely new while the rulebook governing it hasn't caught up yet. Take Beta Technologies as an example. They've logged over 125,000 nautical miles in test flights, real flying across real terrain, not simply hovering inside a hangar for cameras. Their aircraft are legitimately impressive pieces of engineering. Yet in 2025, the company posted losses around $745 million against revenue of just $35 million. Their fixed-wing model targets certification sometime in 2026 or 2027. The vertical takeoff version looks toward 2027 or 2028 at the earliest. Until certification arrives, every aircraft they fly operates under an experimental certificate, meaning you cannot legally charge anyone for a ride. You can test it, showcase it, let pilots try it out, but you cannot build an actual business around it yet. Compare that against the RX-4E, already holding full commercial certification and already carrying paying passengers. Then there's Buy Aerospace, which started taking flight school deposits back in 2018. Their 4-seat electric trainer was supposed to fly by 2021 and reach certification by 2023. Real schools, like Spartan College of Aeronautics, placed real orders and paid real deposits based on those promises. But by mid-2026, that certification timeline had slipped all the way to 2028. The schools that paid deposits years earlier are still flying old Cessnas today, still pumping leaded fuel into them, still waiting on a plane promised half a decade earlier. That gap between these two outcomes is massive, but it's not because anyone is bad at their job. Aviation certification ranks among the toughest regulatory gauntlets on the entire planet. The FAA simply doesn't have enough staff who deeply understand electric propulsion systems yet, given how new this technology genuinely is. The rules governing electric aircraft throughout the West are still being written from scratch, and the framework allowing electric planes onto commercial routes keeps slipping further out with each passing year. It's a real institutional bottleneck, and it's hard to fault anyone directly, since the entire system was originally built around conventional aircraft, not battery-powered ones. Think of it this way. Invent a new kind of car, and you can drive it on existing roads under existing laws immediately. No new rulebook required. But invent an airplane with a propulsion system no regulator has ever certified before, and those rules simply don't exist anywhere yet. Somebody has to draft them entirely from nothing. Aviation rulemaking crawls forward slowly because every conceivable failure mode has to be fully examined and resolved before approval gets granted. The team behind the RX-4E never ran into this particular wall because their regulator was already prepared to move alongside them from day one. That single difference reshaped the entire trajectory of the project. But here's what's interesting about bottlenecks generally. While one group sits stuck waiting, somebody else may already have found a completely different route to the identical destination. And this particular story starts much earlier than most people would guess. The research lab behind this aircraft was mentioned briefly, but their journey actually began years before the RX-4E ever existed as a concept. Back in 2015, this same institution, based in Shenyang in northeastern China, accomplished something that arguably deserved global headlines at the time. they certified the world's first electric airplane. Not merely built one, not merely tested one, fully certified it for actual operation. A two-seat electric aircraft called the RX-1E received a complete type certificate from the Civil Aviation Administration of China. While Western companies were still showing investors polished concept renderings, this team was already flying a certified electric plane on genuine missions. That first aircraft was modest, seating 2, offering limited range, mainly built for training purposes rather than commercial use. But it was real, legal, and actually airborne day after day. That was merely the warm-up act. Over the following 9 years, the team refined everything they'd learned, building the RX-1E. Better battery systems, holding more energy and lasting considerably longer between charges. Smarter control software managing power distribution with far greater precision. Sharper manufacturing capability overall, including learning to build airframes from carbon fiber, the same ultra-lightweight material found in Formula One cars and spacecraft. Perhaps just as critically, they built a cooperative relationship with their aviation regulator rather than an adversarial one from the start. Throughout the West, relationships between aviation startups and regulators often grow tense, with companies wanting to move fast and regulators wanting to move cautiously. In China, the regulator participated throughout the entire development process from day one, not merely showing up at the final approval stage to check boxes. That meant when certification time arrived for the RX-4E, nobody was blindsided by unfamiliar technology. The regulator already understood the underlying systems intimately, having watched them mature gradually across an entire decade of testing. The first RX-4E prototype flew in October 2019. Over the following 5 years, 3 separate prototype aircraft logged more than 1,200 flight hours combined and completed 1,800 takeoffs and landings. A serious testing program by any reasonable measure. They flew through every kind of weather imaginable, at varying altitudes, with different payload configurations tested repeatedly, pushing every system toward its breaking point and fixing whatever failed along the way. Then, on December 29, 2024, the Civil Aviation Administration of China granted the RX-4E a full type certificate under its CCAR 23 standard, closely mirroring the FAA's Part 23 certification used for normal category aircraft in the United States. Here's why that distinction matters so much in practice. This wasn't some light sport certificate carrying a stack of operational restrictions. This was full commercial certification, plain and simple. The RX-4E can legally carry paying passengers on commercial flights right now, making it the first 4-seat all-electric aircraft anywhere on Earth to reach certified commercial status. Not someday down the road, not pending further review. Today. In April 2025, the RX-4E showed up at an international air show in Germany and won an award recognizing excellence in electric flight design. A company called Volare Air Mobility, based in Hong Kong and handling global sales for the aircraft, had already finalized a deal delivering 20 aircraft to an Indian aviation company. That deal was valued at $12 million total, roughly $600,000 per plane, placing it directly in the same price range as a brand new Cessna 182. Step back for a moment and look at the complete picture here. A research lab tied to a Chinese university designed an electric airplane from the ground up, achieved full commercial certification for it, showcased it internationally at a major air show, won an award for the achievement, and signed a legitimate delivery contract with a legitimate paying customer. All while Western startups backed by hundreds of millions of dollars in venture funding remain stuck waiting on regulators to finish drafting the necessary paperwork. And we haven't even reached the most interesting part of this story yet, the specific engineering choice that turns this from an impressive headline into a practical, usable tool. Let's break down the core physics problem behind electric flight in plain terms. Batteries are heavy relative to the actual energy they store internally. Aviation gasoline packs roughly 12,000 watt-hours of energy per kilogram of weight. The best Aviation batteries available today hold somewhere around 250 to 300 watt-hours per kilogram. A massive gap by comparison. Line those numbers up side by side, and gasoline holds roughly 40 times more energy per pound than a battery currently does. That enormous gap is the central reason electric flight has proven so difficult to achieve at scale, and why experts spent years insisting electric airplanes would never scale meaningfully beyond small hobbyist drones. So how do you actually get around that fundamental limitation? You design the entire aircraft to squeeze every last drop of available energy as efficiently as physically possible. The RX-4E's wings stretch 44 feet from tip to tip, actually wider than a Cessna 182's wingspan. Those elongated wings exist specifically to cut drag, the resistance force air creates against the plane as it moves forward through the sky. Less drag means less power required to stay airborne, which directly means the battery charge stretches considerably further per flight. Think of it like cycling down a smooth road. A lightweight road bike with thin tires glides easily across pavement, because relatively little resistance holds it back as you pedal. A heavier mountain bike with wide, knobby tires demands considerably more physical effort to reach that same cruising speed. The RX-4E is engineered like that road bike specifically, with every curve and surface shaped deliberately to minimize drag and stretch the battery's limited reserves as far as physically possible. The electric motor itself, built by Slovenian company Pipistrel, converts electrical energy into forward thrust at over 92% efficiency, an extraordinary figure. A traditional gasoline engine inside a Cessna converts merely about 25% of its fuel energy into usable forward power, with the remainder lost entirely as heat, noise, and vibration. Sit with that comparison for a moment. A gasoline engine wastes roughly 3/4 of the energy you actually paid for at the pump. The electric motor wastes less than 10% of its input energy. That's not a marginal improvement worth mentioning briefly. That represents an entirely different tier of mechanical efficiency altogether. But the feature that actually changes the whole equation, the one making this aircraft practical for daily commercial use, is the battery swap system built into its design. When the RX-4E lands, the pilot doesn't sit around waiting for a lengthy recharge cycle to complete. The battery pack sits within an easily accessible compartment toward the rear of the aircraft, deliberately positioned for quick access. Ground crew can pull the depleted pack and slide in a fully charged replacement within roughly 3 minutes total, 3 minutes to completely refill the entire energy supply and get airborne again. Consider what that means in practical everyday terms. Electric cars often need 30 minutes to a full hour for a proper fast charge under good conditions. Western electric aircraft makers have had to spend millions of dollars installing specialized high-power charging infrastructure at airports, specifically because their planes can't swap batteries this way. The RX-4E needs none of that expensive infrastructure whatsoever. All you really need is a spare battery pack slowly charging off a regular wall outlet over a few hours, while the plane keeps flying, using a completely different pack in the meantime. For remote airstrips throughout rural India, island communities scattered across Indonesia, or mountain towns tucked into Malaysia, that's not merely a minor convenience worth noting. No power grid upgrade needed anywhere nearby. No specialized charging hardware required on-site. No multi-million-dollar construction project necessary before operations can even begin. Now for the number mattering most to whoever's actually signing the check at the end of the month. The battery holds roughly 69 kilowatt-hours of usable energy. At typical electricity rates of 10 to 15 cents per kilowatt-hour, a full charge costs about $10 total. The Cessna 182, by comparison, burns $98 hourly in fuel alone before anything else. The advertised total operating cost for the RX-4E lands somewhere between $40 and $60 per hour, against $150 to $250 for the equivalent Cessna. For a flight school running 5 planes 4 hours daily across 6 days weekly, that gap compounds into hundreds of thousands of dollars saved annually. Even battery replacement, needed roughly every 2 to 4 years under sustained heavy use, runs about $10,000 to $14,000 total. Compare that directly against a Cessna engine rebuild, costing $30,000 to $50,000 on a remarkably similar timeline. The battery costs meaningfully less, and swapping it out doesn't mean grounding the entire plane for weeks while awaiting a certified mechanic's availability. But building a great airplane represents only half of the overall battle here. Getting it into customers' hands across the entire world requires an entirely different skill set altogether. And this is precisely where the strategy behind the RX-4E turns out to be remarkably clever in execution. China maintains bilateral aviation safety agreements with both the FAA in America and the European Aviation Safety Agency, letting an aircraft certified within China undergo a meaningfully accelerated validation process elsewhere. The receiving country isn't starting completely from zero in that scenario. They're reviewing test data China already approved and determining what, if anything, still needs addressing to satisfy local regulations. So the RX-4E isn't shut out of Western markets entirely. It's simply waiting patiently in line, backed by 5 full years of certified flight data supporting its case. But Volare Air Mobility isn't merely sitting around passively waiting for Western regulators to eventually catch up on their own timeline. Their approach is considerably more proactive and aggressive than that. They're building customer bases everywhere else across the globe first, strategically and deliberately. In late 2024, Volare announced a joint venture alongside an investment firm in Abu Dhabi and the UAE's General Civil Aviation Authority, constructing an assembly facility there from scratch, with the first phase scheduled to open in early 2026, and production climbing steadily toward 200 aircraft annually over a 5-year period. Why does that particular location matter so significantly to the overall strategy? An aircraft assembled within the UAE avoids tariffs currently targeting Chinese technology exports directly. It carries UAE certification authority instead of Chinese authority alone, and it ships from one of the most well-connected logistics hubs found anywhere on Earth, sitting precisely at the crossroads of 3 separate continents, reaching markets across Africa, Europe, and Asia considerably faster and cheaper than nearly anywhere else on the planet. Beyond just the UAE, they've signed agreements with aviation partners throughout Malaysia and Indonesia, covering regional operations, and they're actively pursuing pilgrim transport contracts within Saudi Arabia, a market generating thousands of short regional flights every single year without fail. The Hajj and Umrah pilgrimages bring millions of travelers into Saudi Arabia annually, many needing short hops between nearby cities situated relatively close together, exactly the kind of route where electric aircraft shine brightest. Even a small fraction of those flights shifting toward electric power represents enormous untapped market potential. And remember that Indian deal mentioned earlier? 20 aircraft, $12 million total value. For a country where pilot training is expanding rapidly and infrastructure gaps remain real, a plane costing $10 to fuel and requiring no specialized charging setup whatsoever isn't merely a luxury item for wealthy buyers. It's a solution perfectly suited to that particular country's exact circumstances. Step back once more, and the overall strategy becomes completely obvious in hindsight. Build the market first in regions ready right now. Accumulate millions of hours of real-world flight data along the way through actual paying operations. Then, when the moment finally comes to approach FAA and European certification bodies, arrive carrying a track record that's difficult to dismiss. Rather than fighting for Western approval first and building a market second afterward, they flip the entire traditional sequence around. Build first, prove it works reliably in the real world, then let the accumulated data speak for itself. This plan is already paying off in measurable ways. While Western startups keep trying to convince cautious regulators, the RX-4E is already flying real customers who are ready and willing to write checks immediately. The Cessna 182 won't vanish from the skies overnight, of course. That's simply unrealistic. Thousands of piston engine trainers remain flying worldwide right now, representing billions of dollars in accumulated investment and decades of built-up supporting infrastructure. Mechanics who've spent entire careers specifically on Lycoming engines, fuel suppliers, parts distributors, and insurers, all financially dependent on keeping these older planes running smoothly. That entire ecosystem won't simply disappear overnight. Aviation as an industry shifts gradually by nature, rarely all at once. Wooden propellers gave way to metal ones gradually over multiple decades. Open cockpits became fully enclosed cabins gradually over many years, too. But the starting gun has already fired regardless of that historical pace. A flight school weighing 2 new Cessnas in 2026 now has a solid certified alternative available at essentially the same purchase price, one that slashes ongoing operating costs by more than half immediately. That particular option simply didn't exist even a single year ago. Now it does. The RX-4E carries real limitations worth acknowledging honestly, rather than glossing over. Its range sits around 162 nautical miles on a full charge. Its cruising speed lands around 108 knots, noticeably slower than a Cessna cruising at altitude. But flight training rarely demands extensive long-distance range in practice. A typical training lesson leaves the home airport, practices maneuvers within a local area nearby, and returns shortly afterward, often covering roughly 100 nautical miles total distance. For that specific use case, 162 nautical miles of range isn't a limitation at all in practice. It's more than sufficient for the job at hand. The overall direction here seems unmistakable at this point. When a certified electric plane exists at essentially the same purchase price as a traditional one while costing merely a fraction to operate per flight hour, the underlying numbers speak entirely for themselves. If this video shifted how you think about electric aviation, hit that like button, subscribe, and turn on notifications so you never miss what comes next. And let me ask you this. If you ran a flight school tomorrow and had to choose between a Cessna and the RX-4E, which one are you buying? Drop your answer in the comments below.